So, Chapter 6 is thermodynamics. Thermo meaning heat, dynamic meaning change. Okay? And before we can really get into the nitty-gritty of this chapter, there are a lot of definitions that we have to get straight to begin with. Okay? So the very first definition we have to get straight is the definition of system. A system is the area under consideration by the scientist. And the surroundings is everything else. Okay? So for example, suppose I want to study the deer population. Okay? Well, I want to study the deer population of Dane County. Well, in that case, my system would be Dane County. And then everything else would be the surroundings. So that would be, the rest of the state or the rest of the country. All right? Now, maybe I'm not interested in just Dane County. Maybe I'm interested in the deer population of the state of Wisconsin. In that case, my system would be Wisconsin, and the surroundings would be the rest of the country. Okay? So the scientist gets to determine whether or not what is the system. Okay? Now you can have a closed system, and a closed system is where there is no exchange between the system and the surroundings. Okay? Whereas an open system means that there is an exchange between system and surroundings. So let's take our deer population of Wisconsin example. So here's my horrible picture of Wisconsin. So I'm studying the deer population of Wisconsin. That's my system. Now, can deer leave Wisconsin? You bet they can. They can cross over into Minnesota. Can deer enter Wisconsin? You bet they can. So this would be considered an open system because there can be an exchange between the surroundings and the system. Okay? Now, what about Isle Royal? Isle Royal is an island up in Lake Superior. Now, can deer get off the island? No. Can deer get into the island? No. So that would be a closed system. Now, almost all systems are open, but sometimes we pretend that they're closed just to make the math easier. Okay? So, like when we do science, very often we pretend that energy is not leaving the system, because then it gets more complicated if we do. Okay? Another definition is a state function and non-state function. Okay? So a state function is path independent. A non-state function is path dependent. Okay, so let me give you an example of a path dependent variable. Okay, so let me draw my horrible picture of the United States. Okay, so the Great Lakes. So here we are in Madison, and I want to go to Denver. Okay. What is the distance from Madison to Denver? Now, someone might say, oh, okay, that's easy. The distance between Madison to Denver is 1,000 miles. But someone says, no, that's not the distance. The distance is 2,000 miles. You're like, how is the distance 2,000 miles? Well, you didn't specify the path. It is possible that you would drive down to New Orleans first and then drive up, and this would be a distance of 2,000 miles. So distance is path dependent. Okay? Oops. Now, how about a different scenario? What if I asked you about altitude? Madison is at 300 feet above sea level. Denver is 5,260 feet above sea level. So if I asked you, what is my change in altitude when going from Madison to Denver? Okay, well, if I go from 300 feet to 5,260 feet, my change in altitude is going to be 4,940 feet. Okay, that's my change in altitude. Well, what if I drive down to New Orleans first? New Orleans is actually below sea level. It's minus 4 feet. So if I drive down to New Orleans and then up to Denver, what is my change in altitude? Well, guess what? It doesn't matter, because where do I end up? I end up at 5,260 feet. I started at 300 feet. So the fact that I went to minus 4 first and then went up, my change in altitude is still the same. I started at 300, I ended at 526, so my change in altitude is still 4,940. So altitude is path independent. Okay, so state functions, and I'm going to list them for you. They may not seem all that, they're not going to mean anything to you right now, but I'm just going to list them all. These variables are state functions. Delta H, delta S, delta G, energy. Some textbooks use U instead of E, so delta U is the same thing as delta E. Those are all state functions. Non-state functions are work and heat. The variable for heat is Q. It's a bad Q. Okay, so let's take a look at why work is a non-state function. Well, the definition of work is force times distance. Okay, so if I have a little wheelbarrow here and I want to carry a weight, now which would be the better path to go? Should I go over this mountain, or should I go around the mountain? Well, which is the longer distance? If I go around the mountain, my distance is going to be 10 meters. If I go over the mountain, my distance is going to be 30 meters, and I am going to require a higher force. So obviously going over the mountain is going to be more work than going around the mountain, even though I'm ending up in the same destination. Okay? So work is a non-state function. Now in science we're not so interested in this definition of work. We're more interested in this definition of work. Work is negative P delta V. We're more interested in the work done by pistons and gases. So when my piston goes down, my change in volume will be negative, and that means that my work is going to be positive, because a negative times a negative gives me a positive value. Okay? P is pressure. The piston is my system, everything else is my surroundings. So when work is positive, we would say the surroundings is doing work on the system, meaning you have to put work in. But in the opposite scenario, here's my gas. If the piston is going up, it means that my change in volume is positive. Therefore, my work will be negative. And then we would say that the system is doing work on the surroundings. So let's just do a quick problem here. So let's say the piston expands from 200 milliliters to 800 milliliters at a constant pressure of 50 kPa. What is the work done? So these problems may seem easy, but they're actually more difficult than you think. So the initial volume is 200 mils. The final volume is 800 mils. My pressure is 50 kPa. Now my volume must be in liters. So I have to convert this to liters. Pressure must be in kPa. So if they give you pressure in atmospheres or anything else, you must convert to kPa. So my change in volume is going to be my final minus the initial. always, anytime you take a delta, it's always final minus initial. Don't let anybody tell you anything differently. It's always final minus initial, never the other way around. If someone tells you you can subtract the final from the initial, they're wrong. It's always final minus initial, not initial minus final. So 0.8 minus 0.2 gives me 0.4. So then negative 0.50, I'm sorry, negative 50 kPa times 0.400 liters would give me negative 20 liters times kPa. Well, a liter times a kPa is equal to a joule. That's something to remember. A liter times a kPa is a joule. So my answer would be negative 20 joules of work has been done. Work and heat are always measured in joules. Okay? So that's the way you calculate work. That's the equation that we're going to be using. This guy up here, I will highlight it. Okay? It's important to know that when work is negative, when work is positive, and that a liter kPa is a joule. All right, have a good night.